All right, hello everyone. Today I'll be covering the disjoint sets. So yeah, if you saw the other video for this section review, it was on some MST algorithms that we introduced. One was called prims, one was called Kruskal's. And if you saw in Kruskal's algorithm, we did something where we were kind of like continually checking like, are two vertices in the same like component, quote unquote. And this is where like, you know, if you kind of think about like this problem, like are two things in the same component or are two things connected? It's kind of hard. Like what we really want to kind of know is like, are they part of the same like set of vertices? And so what we're going to do is introduce this new data structure that really is like super specialized. Like the only thing that we'll really use this data structure for is just to kind of like keep track of different sets of vertices and like be able to like merge them together. Like you can think back to Kruskal's algorithm, like when we merged, you know, when we chose an edge, we would kind of like merge both of their components like together into one component. So this is like the high level idea is like we're going to use these disjoint sets to do this. But yeah, let's get into like what is a disjoint set first. So as like a review, a disjoint set, the disjoint set ADT, it's basically a collection of like smaller sets is sort of how you can think of it. Like there's one disjoint set with like multiple smaller sets in it. And really we support these like three main operations. There's an operation makeSet that takes in you know, a number or a member and it creates a new set in the disjoint set, so like a new mini set where the only member here would be X. And this is also what we call the representative for the set. I'll talk about that in just a minute. Find set we can also do, so you can look up like, hey, if I have a value X in my disjoint set, like what set is it part of? So it looks up the set containing element X and it returns this representative of that set. And I guess going back down to this picture down here, like what we mean by representative is what we do is we just kind of like arbitrarily have, you know, a node be like the representative of its set. And so what that means is like this 8 here is the representative of this whole entire kind of like mini set in our disjoint set. So you can think of like maybe our disjoint set has like all of these elements, including 2, but we have like 2 mini sets, one where 8 is the representative and one where 2 is the representative. So this find set, it just returns that representative. So you can think like if I wanted to know if like 1 and 13 were in the same set, I could basically call find set twice and compare the representatives, right? So I could call find set of 1, that's going to return 8 because it's going to keep going up this tree until it can't anymore. So I jump to 8 and then I can't jump up anymore because 8's not connected to anything. So I just say 8's my representative. It's at the very top of this disjoint set. And then also 13, like I'd start at 13, jump up, you see 8. And so you know that 1 and 13 are part of the same set because their representatives are the same. If I ask for 2's representative, again, I'm going to do that same process where I kind of start at this node, keep going up until I can't anymore. As you can see, I can't go up from here, so the representative would just be 2. So basically, you can kind of see how all of these nodes are going to have the same representative because you're just always jumping up until you can't any longer. The third operation that we support is union. That basically, it looks up the set containing X, looks at the set containing Y, and then it combines those 2 sets into one. And the way that we do that is you actually combine the 2 representatives. So you know, in the most naive form, you would just kind of like arbitrarily choose one representative. Like let's say 8, we just are going to choose 8 to be the new representative, and you would just point 2 at 8. So you just point the representative of one set at the representative of another. And notice that there can only be like one representative of each set. So really this union operation, like once you find the representatives, it's like a constant operation, right? Because all you do is just assign one representative, like the up pointer, to another representative. Lots of saying the word representative. Let's get into an example. It might be more helpful here. Yeah. So yeah, like the big idea for like Kruskal's, if you kind of remember, like we're always kind of wondering like are 2 elements part of the same set or part of the same component? And we kind of, you know, I talked about how you can use this find set to figure it out, right? If I called find set of 1, find set of 7, it's going to do that thing where I start at this node and keep going up until I can't any longer. And you see that both of them are 8. So you know that 1 and 7 are part of the same set here. Here's the union operation that I was talking about. So what you do for union is you first call find set. You do find set twice. So if I'm unioning 1 and 2, I'd first call find set of 1, because I'd say, like, where is 1's representative? I get to 8, and then I stop there, right? Because that's 1's representative. I can't go up any longer. I also call find set on 2. In this case, 2 is already the representative, so it's just there. And then step 2, once we have found both those representatives, like I said, you just kind of like arbitrarily choose one representative and assign, like, you know, in this example, I assigned the 2 to point to the 8. You could have also assigned the 8 to point to the 2. But we're going to get into like some optimizations, like where you'll see like you can see like here, right, when we're sticking one representative under the other, like it's probably better to stick this 2 pointing to the 8, because like if I stuck this 8 pointing to the 2, now basically for all these nodes, I'm going to have to go up like 2 hops to get to the top, right? So yeah, let's get into this optimization here. Yeah, the idea basically that you can think about for these operations like find set, union, kind of like everything that we do with these disjoint sets, like the runtime is bound by basically the height of any like subset, basically. So the idea here is that if possible, we want to keep the height of the set small. Like we want to keep it as small as possible, basically. So you can see here, like if I attach the 8, if I'd chosen to, you know, it's just to stick one representative under the other. If I'd chosen to point 8 at 2, now there's the height of this, like the resulting thing would be height 2. But if I chose the 2 to stick to the 8, the height of this is just height 1. So we're going to use this idea to say like, okay, basically what I want to do is always kind of like point the smaller set at the larger set. So when I'm unioning, after I get the 2 representatives, I'm always going to choose to, like, the one with the smaller size is always going to be pointing to the representative with the larger size. So yeah, this basically just like ensures that we're like staying in like a state where we're not like increasing the height unnecessarily, basically. So yeah, it just makes sense if you have more elements in the set, like it's more likely that you have a taller height is sort of like the idea. So yeah, you know, if you have more elements, it's more likely you have, you know, a larger height. So we should always point the smaller height one at the larger height one to avoid like increasing the height. And if there's a tie, just pick one to be the root arbitrarily. So if there's a tie, the height's gonna have to grow, but that's okay. So yeah, basically, yeah, this is our first optimization that we'll do, is like when unioning, always choose the smaller sized set representative to point to the larger sized set's representative. That's our first optimization. Yeah, I'm gonna skip this for now, but you might kind of be wondering, like, if, you know, for example, we said that we kind of don't want the height to grow, right? So instead of keeping track of the size, why don't we just keep track of the height? It turns out it's really hard to keep track of the overall height of these trees because you can only look up. You can't actually look down, right? So I couldn't like look down from 8 and like look at, you know, like my longest branch or something like that. Like you basically have to like, it's just like a really hard thing to keep track of the height, but it's easy to keep track of the size. So we keep track of the size instead of the height. Okay, so like I said before, right? The kind of main thing that is influencing like the runtime of any of these operations is the height of the tree. So here's our second, and you know, our first optimization, it was to keep the heights small, like hopefully, right? So always point the smaller thing at the larger thing. Hopefully the heights will stay relatively small. Our second optimization that we're going to do is also going to be this thing that's going to keep the height small. What's going to happen is whenever I call find set on a node, so in this case, for example, find set of 15, you can think of like what's going to happen here. I jump to 11, then 5, then 1. Remember, we're always jumping up until we reach something that doesn't have an up arrow. 1 still has an up arrow, I jump up to 0. What you're going to do is take all of the nodes along that path. So, you know, every node that was hit along this path for the find set, we're going to take those nodes, and then after this call, we're going to point all of those to the root. So you can kind of think, you know, like as we're going up, maybe we'll like keep track of the nodes that we saw along the way and then point them at the root at the end. And what you'll see, I guess, we don't like expand this out, but what you'll see is like the height actually gets smaller now because Now instead of having this like branch that's like 1, 2, 3, 4 height, our max height once we connect everything here is actually only 3, because I think it's like 1, like 2, 3, for example. There's not like the height actually decreases. And you can think like if I called find set of like 11 after this, it's going to be really fast because it's just going to point right to the 0. So yeah, this adds on like a maybe like constant factor cost to find set, but yeah, it makes like subsequent calls like really fast. So we definitely want to do this. And those are our 2 optimizations. Is that this first optimization with the union by size, and the second optimization with path compression.